All right, good morning, everybody. Welcome to another installment of the SPL webinar series. This week, what we're going to talk about is fundamentals of gas chromatography, specifically how they relate to natural gas analyses. We say that because we'll talk about liquid analyses in a future webinar. Because we're talking about chromatography this time, we decided to go ahead and bring in our subject matter experts for chromatography. So joining me today, I've got Joel Grice. He's our EVP of laboratories. He's over our entire laboratory network. Got Chris Staley. He's our Senior Technical Director of Laboratory Services. Chris is the one who goes around and makes sure that all our laboratories are operating up to SPL standards, troubleshooting, fixes things. So he's our all-around lab know-it-all. Let's use that word. Then we got Zishan Sheikh. For those of you who are on the last one, Z is our petroleum engineer, works in both our technical team and our production allocation. And I'm Dave Curtis. I'm the EVP of strategy and technology. So we'll go ahead and get started here. Okay. So as we go through this, we want you to ask lots of questions. We want you to chime in whenever. Don't wait for the end. Because for those of you who've been in webinars before, if all the mics are open, it becomes kind of a madhouse and lots of background noise. If you don't mind, use the Q&A and click on there within your Zoom panel, ask a question, and Z will ask that question for you. You might notice today that if you were here last time, that we're a little bit smaller space than we were last time. Our conference room is having issues, so we're sequestered in one of the offices, but this will work just fine. So let's get started. All right, so when we talk about natural gas samples, there's two pieces to gas measurement. There's the volumetric side and there's the energy side, both of which are equally as important. But today we're going to focus on energy, which is the natural gas analysis. The volume side, we're going to cover on the next webinar next month. That'll be our gas measurement 101. Okay, so in order to determine the energy of our gas in this industry, typically we use gas chromatography. There have been other methods used throughout the years, but pretty much everybody settled on doing a GC analysis. Find out what the mixture is within your sample, find out what its individual components are, and we assign heating values to it and get our energy. So, okay, so in a gas chromatography sample, how are we going to separate out our stuff? Each component within our mixture has to have something different about it. For the types of GCs that we use, it's pretty much done by determining the different boiling points between the compounds. Then it uses their molecular weight and the chemical structures. Something has to be different about them in order to separate them out. Okay? At the end, and we're going to talk about this more, we're going to get a chromatogram. And that chromatogram is going to tell us everything about our sample. So what does it tell us? It tells us what compounds are present, qualitative analysis. It does that through retention time, which we're going to get into detail. Retention time is the time in which a peak comes off the column or elutes. And in addition to telling us what's there, it also tells us how much is there, how much is by the size of the peak. And again, we're going to get into that more as we get further in the presentation. Yes, sir.
Yeah. Can you check if the presentation slideshow more? I think it's in the presentation.
Okay, so we're sharing the wrong screen. So I apologize for that right off the bat. So let me change screens. All right, and then we'll do this. And it's still doing that. What's it showing me now?
It's now right.
It's showing the right screen. Sorry about that, folks, for the smaller mode. Okay, so let's talk about our chromatograph. Each chromatograph, gas chromatograph, I guess I should mention, we keep saying gas chromatograph. Whether you're running a gas sample or a liquid sample, it's still analyzed on a gas chromatograph because we're going to put it in gaseous phase when we inject it into the instrument. A liquid chromatograph is something entirely different, and it doesn't necessarily mean that you're running liquid samples on it. So each gas chromatograph has got three basic components. It's got an injector. That's a way to get the goodies onto your column. It's got your column, which does the separation of those goodies. and it's got a detector at the end that's going to see them come through and count them as they pass through it. So your column is a tube. It's a long tube typically made of stainless steel or fused silica glass. And that column's either going to be lined or it's going to be packed with goodies that as our gas goes through it, it's going to interact with and separate. Okay? So that's all fine and good, but how does that all work? So we're going to go through my favorite analogy, and we're going to take a sample. And our sample is going to be a group of people. Our injector, in order to get them all onto column in a single phase, is going to be a city bus. So we're going to drive those folks in that city bus to the end of our column. Our column is going to be Bourbon Street in New Orleans. As most of you, I'm sure, are aware, Bourbon Street is well known for being lined with bars up and down both sides. So that's our column lining. That's what our sample is going to interact with. Okay, so we're going to take those people off that city bus and we're going to inject them onto column. When we inject them, they're going to hit the end of the column all en masse as one whole sample grouped together. Okay. Then, depending on each person's affinity for drinking, they're going to begin to interact with the walls of the column. And as they interact, they're going to start to separate. Okay. So as they go down, non-drinkers, they're just going to walk straight down that street and they're going to go out the other side. We're going to have somebody there with a counter and he's going to count how many people come out in each grouping. So you have your non-drinkers. Someone who drinks a little bit is just going to touch the wall a couple of times, head out the other side, more and more and more till you get to your heavy drinkers that are really going to interact with those walls and come out late in our analysis cycle. You will have people that never ever come off of that street. For those folks, we would have to choose a different column lined with shoe stores or something to that effect that they could care less about, that they're going to move through that column faster. Okay, so now let's take that and let's apply that to a real chromatograph. So let's go back to our block diagram. So here's our block diagram. We have our GC inlet column detector. But let's straighten that column out. Let's put it in a straight line so we can see what's going on. Okay, we mentioned that our chromatogram is the picture that tells us what's come through and how much. So we need to add a chromatogram to this. Okay, so let's inject our sample onto the end of the column. It's going to inject as one whole mass again. As we inject, it's going to start drawing the baseline on our chromatogram. Okay. As that sample works its way through the column, it's going to begin to separate. After we get it separated, hopefully, it's going to start entering our detector. As each compound hits our detector, we get a peak on the chromatogram. That's what we're going to call compound A. It's the first compound to make it through. Then our second compound, it keeps coming through, hits our detector. Our third compound keeps going for however many compounds we have in there. And we wind up with our completed chromatogram. Okay, so in essence, that's how they work. So, all right, how are we going to set that all up? Well, in order to do it, we've got to have a properly developed method. And anything to add? Is this? You're good? Okay, just making sure. Everybody's quiet behind me. So anyway, a properly designed method. So we've got to have resolution of the desired compounds in a timely manner. We've got to have a properly integrated peak. We're going to talk about what that is. We're going to have to identify each one, and then we're going to have to find out how much of each one is there. And we're going to have to develop a method in order to make that happen. And so depending on your analysis, you're going to have different methods. So for instance, we're talking about natural gas analysis here. So you'd have GPA 2261, which goes out through C6 plus or C7 plus. And you have GPA 2186, which is extended analyses. We'd have to have different setups for each one, different method development for each one. Okay. So peak resolution. When we look at this, first of all, we need well-defined sharp peaks. So when each compound elutes through the detector, we want to have a nice sharp peak, a peak that preferably starts at the baseline and then goes up and ends back down at the baseline before another peak starts. Okay. Now, sometimes when you've got, depending on your setup, you can't get quite baseline to baseline resolution. And so we have to live with something where the next peak starts before the first peak finished. That's not a problem. We have to settle for that. We're going to talk about how to properly integrate that. But our second picture down there, we could live with that. The third picture is what we call coelution, is where peaks are stomping on one another, two or more peaks. That's something that we can't live with. If you look at that third picture, there's no way to pick out the individual compounds and properly determine how much of each one is there. Okay. So peaks must have a defined start and stop. When we look at the pictures here, the one on the left, where it says not perfect but usable, not perfect is an understatement. That peak stinks, but if we had to, we could use it. We have to make sure it's integrated properly. This integration is what's called a tangent skim, where we're going from the valley to baseline, and we're picking just that peak out because it's on the tail of something else. The one on the right is completely unusable. There is no defined start. There's just kind of a slight deflection in it as it's going up. So you don't know where one thing starts and another thing begins. So be careful of this. There are instruments out there that were professing that this was okay in order to get fast analyses times. Fast, we all want to get it done as quickly as possible, means more throughput, means if you're in a lab, you can get more samples for the day. If you're in the field, you can get done with this location and move on to the next one. We want it done fast, but we can't sacrifice accuracy and quality for that speed. There's an old saying, you can have fast, good, or cheap. Pick two. You can't have all three. So, all right. So we look at our start and stop and our integration. That integration is crucial to get accurate amounts. So as we mentioned, we should, if we can, start from where the flat of the baseline first starts to head up into the peak and end after that peak returns to the flat of the baseline. We sum up the area under that curve, and that's how we're going to determine how much of that compound is there. Okay, so looking at that a little closer, we've got a start peak, a stop peak. We've got our integration line, which goes between the two. That gives us our area. Okay, so if we don't have our system set up, we can inaccurately account for the area under that curve. So this is under integration, what's called peak shaving. In the old world of, I shouldn't say old world, in the other world of environmental, this would actually get you jail time. So you don't want to do this. So the start of the tick is too high up on the shoulder. Actually, the peak has started before it clicks there. And then we have our stop tick down the line. As you can see, we're missing a whole bunch of area in that peak that should be included in the total amount. And then we are picking up area above the baseline as it goes towards the stop tick. And depending on your chromatography software, that could be subtracted, that could be added, that could be missed entirely. So there's all kinds of things that can happen with this. But when we do this, we're going to wind up with an inaccurate amount, an inaccurate area. So we're not going to get an accurate concentration. If your standard, your calibration standard, which we'll talk about, if it was exactly the same amount as this particular compound and you ran it, you would get quote unquote an accurate sample. That's why if you run a calibration standard and you've got improper integration like this, and then you run that standard again, you're going to hit when you run your standard because it's looking at exactly the same thing in exactly the same way. But then when you run an unknown, it's going to be wrong. Does that make sense? Anything to add there? Okay. I passed. Yay. All right. So that was under integration. Let's look at over integration. So with over integration, we have some sort of baseline artifact that has us have a start tick too soon. And so it's lower than where that peak actually starts. So we draw that line, what we wind up is with a whole bunch of area underneath that curve, which isn't part of the peak. And so we over integrate, we overestimate how much is involved in that peak. If you look at the picture to the right, This is how that peak should actually be integrated, as we talked about earlier. This is called a tangent skim, where we go from the valley to the baseline to make sure we're only getting that peak and not getting extra fun in it. Again, if I was to calibrate like this and then run my standard, my results would come out correct, but that doesn't mean it's right. Make sense? Okay, so peak integration. We talked about earlier that sometimes we have to live with a baseline, valley baseline. And so that's what we have here. We go from baseline, but before the first peak gets back to baseline, a second peak starts. In this case, it's isonormal butane. Very common for these two peaks to have slight coelution, but we have enough separation to be able to split them out. Proper integration would be to do a valley split, which would be to split straight down from that valley to the baseline, as we show on the left side. Improper integration would be to take it up to the valley and then back down again, separating those peaks out. Once again, there's some manufacturers out there that have done this specifically because it makes their repeatability numbers work great. Because again, if I run the same sample over and over again, I'm going to get the same value. And this worked better, but this is improper integration. As your concentrations change, you're going to get inaccurate values on your actual unknowns. Okay. So backflush, Chris, you want to tell us about backflush systems, sir?
Yeah, backflush systems are designed to separate the heavier compounds on natural gas samples, typically hexanes plus. The peaks are lumped with the backflush, and some of the bullet points on the backflush systems that we have, and they're common to a lot of our instrumentation, from the 2177 procedures to the 2261 for natural gas. The hexanes plus can include up to 150 compounds and can run out as far as C14. The identification and quantification of the individual compounds, when they're not required, the backflush is very important because it can greatly speed up the analysis. And you'll see in the next few slides the backflush timing, and these are the world's fastest analysis, I swear. And we'll try to talk through them, but you'll see the flow through the valve system and how the backflush works and how it doesn't work when the timing isn't set appropriately.
You know, if we can make a GC that ran as fast as what we're about to show them, we could all retire.
That's right.
Just saying. Okay. So, Chris, as you said, this kind of goes fast. So if you tell me if you want me to pause it, and I will do my best to pause it in the middle.
We'll give it a shot.
All right. So you ready for me to hit go?
Go.
All right.
So the sample gets injected onto the GC. The gas flows to the pre-column where the initial separation occurs. The lighter compounds continue to flow through the system, and the C6 plus component gets left on the pre-column. As the lighter components approach the partition column, the backflush switches, and the samples still move throughout the column. You can note here that the flow is reversed on the pre-column. The C6 is actually heading towards the detector. The light components continue to flow towards the detector and will rejoin the C6 plus component. And I'm going a little fast. As the components hit the detector, the C6 plus hits first, followed by the lighter compounds. The C6 plus and the lighter compounds follow, or the lighter compounds follow a boiling point distribution, and the C6 plus hits first. It is the heaviest compound, but because of the valving and the reverse flows and the backflush technique, it's allowed to hit the detector first. The second illustration here is a backflush timing that is too soon. Sample's injected on the GC again. Sample flows towards the pre-cut column. Sample begins its initial separation. The C6 is retained within the pre-cut. The lighter compounds flow towards the partition column. The backflush switches, and this time you'll notice that part of the normal pentane is flowing back in the direction of the C6 plus component. That normal pentane will combine with the C6 plus as the lighter compounds continue to flow to the detector. The C6 plus, including the normal pentane, will reach the detector first, followed by the lighter compounds in the boiling point distribution. The thing to note here is that the C6 plus will likely be over-reported due to the fact that the normal pentane has been improperly backflushed with that component. With that said, the normal pentane will also be diminished on the analysis. The last simulation here is the valve turning too late. The sample gets injected onto the GC, again follows the same path to the pre-cut column. Sample begins to separate. Sample flows to the partition column, and you can see the tailing C6 peak here. The valve switches too late, capturing some of the C6 component, the lightest C6 component, with the lighter compounds. The flow is again reversed. You see that the C6 components in the pre-column are combined. The C6 plus minus the lightest C6 component reaches detector, followed by the lighter compounds. In this simulation, the C6 component would be underreported, and the normal pentane could potentially be overreported in this simulation.
And that, or that it's potential that light one may never even get seen.
That's right.
Yeah, whichever ones make it through, if you're not quantitating them, they're just gone.
Right.
Yep.
We have a question from Tim. So he says, we used to integrate after each run and correct for the baseline gaps. Who does the best at doing this automatically? Who does SPL suggest using GCs?
Ask that again. I apologize. And who's it from?
Tim,
Hey, Tim.
who does the best? So he says we used to integrate after each run and correct for the baseline gaps. Who does the best at doing this automatically, and who does SPL suggest to use in GCs?
Oh, so if I'm understanding your question correctly, you're asking which software program does the best job at when you set up your integration parameters that it catches it every time and you don't have to go in and make adjustments from run to run to run. I'm going to start out and I'll let the guys chime in. It's a tough one to say because it really has to do with changing of concentrations. You know, some software packages don't do a good job as peaks change sizes at all. Others will, but if you really have something significantly different than your calibration standard, you're likely going to see differences. There's all kinds of other problems with it being different from your standard that we'll talk about in a bit, but that's a potential issue. As far as picking one that's best, I don't know that we're the best ones to say that because, you know,
Small.
yeah,
we use multiple products.
yeah, exactly. Some GCs have proprietary, and so you have to use those. Others, you know, have packages that a person likes because it links up with their limb system. Others have, you know, all those. So your thoughts?
I think what we see mainly is it's the instrument operation itself, the fact that columns that we use these days aren't as good as they used to be. Separation isn't as wonderful as it used to be. Those kind of things add to the difficulty in the proper integration and the timing of those components coming across the instrumentation.
I think on the software, the key, they all have their own algorithms and mechanisms for determining start point and stop point for the peaks. I think really what it comes down to is the process or the ease with which you can set those parameters in the software. Some have really nice automated ways to do that. Others let you do it manually, depending on what you prefer. You can pick something that works for you. But Chris is right. We use probably 4 or 5 different software products, and each one has their own pros and cons. So I think it comes down to how you like to operate, and whether you like to allow the software to do it for you, or whether you like to have more input into determining, yeah, that's a peak as opposed to background noise on the baseline.
So, by the way, I know that we're in a different room here, so if for some reason you're having a hard time hearing any of us, please send something on the Q&A to Z, and we'll get that fixed. So I just want to tap on a couple things. One, the manual integration. Manual integration, for those of you who haven't operated it, is where, you know, the software doesn't quite get it right, so you go in and you manually draw that line. And there's a lot of schools of thought of whether you should or should not manually integrate. As long as it's all traceable and it's all in your audit trail, don't worry about manually integrating. Most of the softwares will downright tell you somebody manually integrated that. So, you know, you can perform just as many shenanigans by having the software do it automatically and changing the parameters as you can from manually integrating. So my personal opinion is, if you like to manually integrate, go for it. You all thoughts?
I have trouble with some manual integration because there's no two operators that will do it the same.
Yeah, depends on the person.
All right, Joel, so the tiebreaker?
I guess it depends on how you like to operate. Like Chris said, I mean, some people that understand chromatography well will do a really good job at it. I mean, if they're used to looking at the examples that you gave with, you know, almost co-eluting peaks and completely co-eluting peaks, I think they can do a good job at it. But it depends on the level of training and experience of the operator.
Yeah, and the key on both of them, whether you're setting up your integration for it to do it right or manual, is you want to make the integration correct, and the number is the number. If you're doing that, you're doing it right. If you're trying to find the number and integrate it so you get the number, now you're cheating. That's the difference.
So one other point I think on that as well is, if you find that you are required to manually integrate every single chromatogram that's coming out in this day and age with the software that's available and the consistency of the equipment, then you probably have something wrong with your equipment.
Yeah.
You shouldn't have to do that. And you're always going to have exceptions where you have an unusual sample or some small glitch, but you shouldn't have to do that on every single one.
Yeah. We have another question from Justin, who's asking, are there any peaks that specifically stand out that we need integrated manually more often than the others?
Interesting, Justin. Again, I think it comes back to the software package. Some are better than others. For me, I would say your carbon dioxide, because a lot of the columns that we use here, carbon dioxide, we're going to have a picture here in a few minutes. When it's a small compound or a small concentration, it'll be Gaussian, meaning it is symmetrical. When the concentration gets higher, it gets asymmetrical. And because of that, some of the software packages will have a hard time integrating it as it changes concentration. Then hexanes plus, you saw some of the ugly hexanes plus peaks we were using in our examples. And if you don't have a backflush and you have a linear system, then as the individual hexanes plus compounds get smaller and smaller, it can have issues integrating those. Anything to add?
No, I agree. Those are the two problem points for those standard C6, C7 type analysis.
Which are the top 3 GCs manufactured today?
Oh my God. Oh, now you're asking us to weigh in on that. Okay. So we're going to, for those of you who also work in the field, you may be a total flow person, you may be a rock person, you may be, you know, it comes down to personal preference. And so I'm going to give my personal preferences, and then we'll go around the room and let others. For a benchtop, I am a Agilent guy, but that's because I've been working with Hewlett-Packard, who became Agilent since the dawn of time, and I just find them to be robust. And you know, you still have 30-year-old 5890s out there that people are still rocking on. So I'm a fan of those. For the portables, I like the Infocon only because they are the evolution of the MTI, which once again, I started out with early on. My business, I based them off of that particular platform. And so I'm a big fan of those.
I'm going to stay on the fence. I think for different reasons, they all have their benefits. If it's working on the instrumentation, doing maintenance, some of them are easier to work on. We have all types and use all types, so I really can't say which one I would prefer over the other.
That's the proper answer.
Are you the brand ambassador? Are you a brand ambassador for one of them?
Yeah.
I don't always agree with Dave, but I agree with Dave on this. I learned on what were back then Hewlett Packards primarily. So I prefer the Hewlett Packards, and the Agilents just seem to be very robust and last a long time. And I've never really used the micros that much, but we seem to have really good luck with the Infocons.
Yep. And that being said, kind of going back to Chris's thing, is it does come down, it's, I'm a Dodge guy, and other people buy a Dodge and it never works for them, so they're a Ford person, or this gal likes a Chevy because she's had the best luck with it. Everybody has a different opinion on this stuff. There's a ton of Shimadzus out there. There's a ton of, Variant doesn't exist anymore. Agilent gobbled them up. But there's a ton of different manufacturers out there, and for specific applications, they really can be the right animal for you, the right price point. That always comes into it.
Well, and I think what's also important is the relationship with the service folks or the help folks at the manufacturer.
Yeah.
If you have somebody who's in your area who's a good service guy or really helpful with application development, that provides a lot of value, because at the end of the day, they're all an oven with a column in them, right? An injector.
Yeah.
So
They all have the three basic pieces. Yep. And so the bottom line is whatever analytical standard you're running, in this case, let's call it GPA 2261, as long as you can hit the precision criteria required by GPA 2261, you're good. Because remember, it's not just that GC, it's the actual column in it. And so no two columns are made the same. Chris mentioned that the columns aren't as good as they used to be. And for those of you who haven't run GC forever, that might go, oh yeah, that's one of those, and I can say this because I am old, one of those old people things that, it's, in my day, they were much better. It actually is the case. For those of you who are chromatography nerds, a interesting fact, the chromosome, which a lot of the columns are packed with and your other components are layered onto, that is the same stuff. It's diatomaceous earth. And so they use it for pool filters. So I'm a diatomaceous earth manufacturer, and I can either clean it for the umpteenth degree and all this money in making it perfect in order to sell it to these column guys that are going to use, a few grams a piece, or I can do very little cleanup and sell it by the hundreds of thousands of pounds to the pool industry. What are you going to do? So it really has changed over the years to where they degrade faster, they don't work as well, on and on. So anyway. All right, peak identification, okay? So, every chromatograph is different, and every set of compounds you're looking for can be different. So you've got to know some things before you start working into identification. First, you got to know what you're looking for. In this case, natural gas, we're looking for nitrogen, methane, carbon dioxide, ethane, propane, isonormal butane, isonormal pentane, and typically C6+. Okay, we know what's in there. Then we need to know what compounds are present. So in natural gas, that's pretty much what's present. So we're good. But if you're dealing with a weird stream, it may have other stuff in there other than your compounds of interest, which can interfere with the compounds you're looking for. The module that each compound we quantitated on, where we're going to look for the compounds, we're going to talk about that in a minute, because a GC may have multiple modules that you're looking for different compounds on each module. Then, of course, you have to know how you're going to do your hexanes plus. Is it backflush? Are you going to do it linearly? So you have to figure all that out when you're trying to figure out for identifying. So let's take a look at a dual module. Okay, a dual module GC, it utilizes a backflush, a lot of them, in order to get that C6+ peak out in a single peak. But we're going to separate out, we're going to do lights on one, and we're going to do heaviers on another. So the key things to remember when you're looking at this is still all the compounds come out on each column. We're just looking at them differently. So as we look at this one, we look at our top module, this is where our lights are going to come out. So first of all, we're going to have that backflush, which sends everything else, all the heavies, out in a single peak. Then our nitrogen, methane, carbon dioxide, and ethane. Then we have our heavies module. Our heavies module, we're going to get that C6+ peak where we're quantitating all our C6 and heavier compounds. A composite peak, this peak is everything that we're quantitating in module 1, all lumped together, all co-eluted in one peak. are propane, isonormal butane, neopentane if it exists, and isonormal pentane. Okay. Here's the same thing, only 3 modules. Difference here in the 3 modules is we keep saying the word nitrogen when we're talking about this analysis. In actuality, it's not nitrogen, it's atmospheric gases, it's air. And so if there is any oxygen in our pipeline, which we hope there's not, it will co-elute with that nitrogen peak on the dual module. So we call it nitrogen, but it really can have nitrogen, argon, helium, all kinds of stuff into that peak. So on a 3-module unit, you can set it up to where you can separate those out individually. Then we get the composite peak, which is everything else. But the key to remember is everything will still come out. So this column that's set up to really separate out those light compounds, the heavier ones are in there, they're just going to take a long time to come out. And the reason why we say that is your analysis, maybe let's call it, it's a micro, and we're going to have a 4-minute run. It may take another 4 minutes before all those heavies make it off that column. So if you were to start a run before they were all off, your next run would have issues because you'd have all the compounds from the previous run still coming off on that individual column. I hope that makes sense. That makes sense? Okay. All right, and then here's a dual backflush. There are some instruments where they take and they put the C6 plus out. Then they break out your mid-range compounds, put those out, then they put their lights. And then what we don't have a picture here of is a linear column where everything just comes out according to boiling point and you keep going until your last compound's out. Okay, so peak identification, how can we determine which is which? Okay, most of the columns in this industry, the compounds are separated out based on boiling point, molecular weight, size, and structure. So you can look at the boiling point of a compound and see where it's supposed to come out. Where things get hinky there is if you have a polar compound like methanol or acetone, they're not going to come out in accordance with their boiling point. They're going to come out in a weird spot. So for instance, methanol on a lot of these instruments will co-elute with your isobutane, even though you would expect it to come out a lot faster. So I've got most of them through boiling point. Now you can do verifications with compound concentration. Methane's your highest concentration. It should be a really large peak. Ethane's your next one. It should be. And so you should be able to look at peak size to determine which is which. If that doesn't work, you can run individual compounds, just run methane, just run isobutane, so that you can see where it comes out in the chromatogram. And as long as you don't change parameters, that's where it's going to come out. Okay, and then the nice thing is in this industry, somebody's done it for us. So chances are somebody's already run this analysis. There's chromatograms in the GPA methods. So as long as you are sticking to same type of instrumentation, same types of columns, you should be able to determine your elution order, which peak is which, from work people have always done in the past. So if somebody else has done it, why do it again? So we talked about that peaks are determined via retention time. So peak comes out, it has a retention time, and we run our standard. We know we've got carbon dioxide, ethane. Ethane comes out at 24.6. That's seconds, not minutes. And so we look at that and we go, okay, now when I run an unknown, I get a peak at 24.6. Is that ethane? Maybe. Is it something else? Maybe. Is it ethane combined with something else? Maybe. And so that's why we have to know what should be in there. In a natural gas sample, ethane, there shouldn't really be anything that co-elutes with it if we had good separation from our standard. And so we should be able to say this is ethane. But if something else funky's in there, it could combine with it. For example, the example we just used of methanol and isobutane. Okay, retention time windows. In your software, you will say, okay, ethane's going to come out at 24.6. And then, but peaks can move a little bit from run to run. So we might say, okay, well, anything from 22 to 26, if a peak falls in there, I'm calling it ethane. So as long as there's nothing else around it and you can set that wide window, you're golden. As peaks move around, you'll be able to identify. And where that becomes important is, we mentioned carbon dioxide. Carbon dioxide, when it's a low concentration, it's very symmetrical, and the peak of it is in the middle of the entire peak. That's wrong. The apex of the peak is in the middle of the entire peak. As that carbon dioxide gets higher in concentration, it becomes asymmetrical, and the apex is no longer in the center. So if I set my window based on a low concentration and I run a higher concentration of carbon dioxide, it could easily step outside my window. And even though I've got this giant peak of carbon dioxide, it may not tell you that it's there. So in that case, you want to widen that retention time window to ensure that you pick it up. Any of that? All right, so what influences our peak identification? Length of column. The longer the column, the more interactions your goodies are going to have with it, the longer they'll take to come out. Column thickness, so how much of the wall thickness, if it's a lined column, what your packing is, that'll also affect the interaction, and that will make it come out slower or faster. Column temperature, we heat up the temperature, everything's going to come out faster. We cool down the temperature, everything comes out slower. Same thing with carrier gas flow rate, is the faster it's moving through the column, the faster the goodies go through, and vice versa. So as we just mentioned, temperature and flow are the big factors that you can adjust in the field. You know, once you pick a column, length, and packing, now it's in there. You're not going to change it from method to method. But you can affect temperature and flow in order to get the desired elution order and resolution that you want in your chromatogram. And with both of them, remember, the higher, the faster, the lower, the slower. You heat it up or crank up the pressure, they'll come out faster, and vice versa. Then we throw in their matrix effects. Moisture is not your friend. And by the way, those of you who people say we can give you a water concentration off of GC, we won't get into it because I could go on for days, but no. So what moisture does is moisture takes up the active sites in the column, and it starts to degrade how that column works. So the more moisture you get on that column, the faster everything's going to blow through. You're going to start losing your peak resolution. You're going to change elution times, that type of thing. Now that's moisture in the gaseous phase. You get actual water droplets in there, and it can really wreak some havoc on your instruments. Okay. Peak size. Peak size is how much it is. We're going to talk about here in a minute. Joel's going to take us through that. Peak size is our sample concentration. The more area, the larger the peak, the higher the concentration of the compound. Again, we'll go through that in a second. Things that affect it is that sample concentration, because as we said, the more it is, the bigger the peak. Instrument stability, baseline noise and detector response. As you get down smaller and smaller and smaller in concentration, it gets closer. If you've never zoomed in on a baseline, it's not this flat straight line that you see in the picture when you've got your full chromatogram. It is a noisy little beast. And as your peaks get smaller, they get closer to that noise, they get harder to pick out. Injection reproducibility. It is critical that you get the same amount onto column every single time. That's why sample valves are a common injector, because they'll have a fixed volume loop. Now keep in mind that fixed volume is only fixed at a given pressure. If you're injecting with a bottle, and this bottle has 40 pounds and this bottle has 600 pounds, it's going to put a different amount into that loop, and you're going to get a different amount on the column. So it's important that you have that reproducibility. If you have a syringe injection and I inject and then Chris injects, we may have the best technique in the world, but if our techniques are different, we're not going to get the same amount on the column. It's just the way it is. Sample stability, is your sample going to remain in a single phase throughout the injection process? And then again, moisture throws us into all kinds of disarray. So I'm going to stop talking for a minute, which is rare for me. And Joel, you want to slide up here and tell us about calibration, sir?
So I'm going to go through this briefly and look at a couple of examples that we have here in the presentation. But the primary thing you need to remember here is that a gas chromatograph is a measurement device. And any measurement device is only as good as the calibration that is utilized to get that device ready for whatever it's going to measure. So that applies to a GC just like it does to anything else that we would use in calibrations, whether in our industry or any. So let's look at a couple of examples, or talk about a few things, and then we'll look at the examples. Basically, the way that we calibrate a gas chromatograph is we introduce a standard of known concentration into the gas chromatograph. It generates a response, as demonstrated earlier in Dave's presentation at the detector. That response is proportional to the amount of component of interest that we introduced. So, and just a quick little example, we'll take 10 mole percent of CO2 injected on the instrument, gets down to the detector, it generates a response of 100 area counts, which is the area under that curve demonstrated with the yellow highlight. So we generate a response factor from that basically is the area counts divided by the concentration. So in our example, 10,000 area counts would be equal to 1 mole percent, because we had 100,000 area counts generated for our 10 mole percent concentration. So you take that to an unknown. Let's say we shoot CO2, we get 200,000 area counts, we divide by the 10,000, gives us a 20 mole percent concentration. So fairly straightforward way to calibrate the GC and generate quantitative values for the components of interest. So again, we're going to go through a couple of examples here of calibrations. You can calibrate your GC with a single point, a known concentration of each component, and run that once, or you can generate a multi-point calibration where you have multiple concentrations of each component that are analyzed in a series, and then use that to quantitate your samples. So the first one, on a single point calibration, we're going to run a single point as indicated in our example. It's 40 mole percent. You're going to plot basically your area counts on your y-axis and your concentration on your x-axis. You take that point, draw a line through the origin, and then extend that out over the range of the concentrations you expect to see. And presuming that your detector is linear, you'll end up with a nice curve with which you can quantitate your unknowns as you move through. So let's say we run our 40%, it gives us a 400,000 area count. We come back and shoot our unknown, generate 600,000 area counts. Using our response factor we calculated earlier, we can then quantitate or come up with a value of 60% for our unknown. Fairly straightforward. So that's all fine and good when everything works perfectly. When you're dealing with a gas chromatograph, we've really oversimplified them. It's an injector, a column, and a detector. There's a lot of pieces and parts and electronics and valving and pressures and pressure control and flow control that are going on. So everything doesn't work perfect every time. So let's look at what can happen with a single point calibration. In this case, we're using, let's say, CO2, because it may or may not be linear over the range of the detector. So let's say we use 10%, because most of our samples we typically see in the range of 8 to 12%. Okay, so we generate our single point, get an area count. In this case, it comes out to 102,000, not the 100,000 that we would expect, perhaps based on our previous example. We draw a line through the origin, extend that out over the range of concentrations we're expected to see, and here's our line. Well, now let's run an unknown at a much higher concentration. In this case, what we would expect to be 60%. It's 600,000 area counts, but when we drop that down, now you're looking at coming up with a quantitative value of only 52%. Clearly, that single point is not adequate for the concentrations over the range of our samples. All right. So how do we address that? Well, you can do what's called a multi-point calibration. And you select a series of concentrations that cover the range you would expect in your samples, or the linear range of the detector. You run all those points, you draw a regression or a linear line through best fit regression through those points. And then you use that to go back, run your unknowns, and come up with quantitative values. So here, when we run this, since we have more than a single point, and we've covered the entire range of the detector, we get 600,000 area counts that corresponds to 60%. So that line may or may not be straight. It depends on what you're doing. And I think in the case of this natural gas analysis, we can pretty much assume most of the time it's a pretty straight line. But depending on what you're doing, that may not be a straight line. So it's very important in those cases that you use a multi-point calibration, which we do on, for example, the alcohols, the ketones, oxygenates. So, all right.
Okay. So now my apologies. I was supposed to change the slide and put a pretty picture instead of a ton of words. So ignore the words, pretend they're not there. So we talked about injectors, we talked about columns, we talked about all the fun that went into calibration. All right, so how do we detect it? There's a ton of different detectors out there, flame photometric detectors, electron capture detectors, mass specs. Some are designed to see sulfurs only, some are designed to see compounds that have double bonds, on and on and on. The most common one for natural gas for a 2261, when you're not doing extended, is a thermal conductivity detector. Thermal conductivity detector is a universal detector that basically sees everything that goes across it. Real easy way of understanding it is it's basically a light bulb filament. Our instrument is telling it to run at a given temperature. When we run our carrier gas across it, which we haven't talked about much in here, but typically helium is the carrier gas. There can be differences. That helium runs across that light bulb filament and it's continuously cooling that filament. Okay, so then we're putting energy into that filament to maintain that temperature, and that's what you're reading on your chromatogram. So then when we run our sample, we'll have a goodie come across. It's being carried in our helium, and let's say methane goes across. Methane has a different thermal conductivity than helium, which means it drags away, in this case, less energy than the helium did, and so it needs less power in order to maintain its temperature, and we see a change from what helium requires energy-wise, power-wise, and what methane does, and that is the peak on our chromatogram. Simple, easy, and bam. One of the big downfalls is if you change carrier gas and you don't tell it, it'll run at a temperature that's too hot for that particular carrier gas, and you blow your filament, and it just costs you a ton of money and a ton of time. But we can talk about that another time. So that's pretty much it. In the end, you wind up with a report that, again, I was supposed to show a better report and I didn't. And so you wind up with a report that gives you your analysis. And we'll go through that. We have a presentation that we'll go through down the road at some point in one of our seminars that talks about, if you're a person who just receives your sample reports, how can you look at that report and determine if it's good? What can be some indicators in that report that tell you there are issues? And we'll go through that at a later date, as well as probably how to calculate heating values. But we're getting close to the end of our seminar, so we want to give time for people to ask questions. So for those of you who want to hang on, and anyone who wants to ask a question.
We have a question from the earlier discussion. One comment from them is, typically manual integration is used more in applications that have trace analysis and push the limits of the software.
Okay, so if you didn't hear that, Vince Rocco, who's, by the way, a great source of information as well, he wanted to point out that manual integration happens when you're pushing the limits of your software, when you're close to detection limits, and those types of things, usually things that are out of the norm. I believe, and Vince, you can tell us if you're wrong, was basically the same as mimicking what Joel was saying earlier, is if you have everything set up correctly, you're running your standard samples, your software should be able to integrate it automatically time and time again without a problem.
From Tim, he says, I had a 30-year-old 5890, and I get a new column that's better and still works on the old ones.
Absolutely. So you have a 5890. Of course, we talked about there's different columns. There's the stainless steel, there's the glass, there's packed columns, which usually are the stainless, and then your capillary columns, which will be the fused silica. You actually can change if you have a packed column GC, you can change that to a capillary GC. It's going to take complete method development changes. Even if you go from pack to packed, you're going to have to make those changes in order to make sure that everything's working properly, because it's no longer the same instrument. Talk to your manufacturer, your column manufacturers, whoever that is, and tell them what you want to do, what your application is. They should be able to recommend the right column to you. They should actually have drawings that show what your elution time should be. And typically they have some recommendations on initial temperatures and valve timing. Keep in mind, instrument manufacturers are notorious for telling you that you use exactly this time and this time for your valve changes. Don't listen to them. Use those as benchmarks, and then you've got to find the sweet spot on your backflush timing. Chris's examples of if you turn too late or too soon, if your column is slightly different, if you're, and I don't mean it can be the same number, but unless it came off the same lot, chances are it's not the same as the one before, and you'll have slight different retention time changes, slightly different, where you've got to adjust your pressure, your temperature, and or your valve timing to get everything out the way you want it. So my long-winded way of saying you absolutely can upgrade things. You can change valving. You can turn it from a backflush to a linear instrument or vice versa. So they're versatile, the big instruments like that, so you can change them to however you need them to work for you. Did you all agree with that? Did I miss anything?
I agree.
Okay.
We still have some 50.
That's right.
Question from Justin is asking, can you explain what a pore plot column is and its functionality?
Okay. So a pore plot is a packed column that's typically used for the front end of a hexanes plus, or for the front ends of your natural gas analysis. When you're not trying to separate out the atmospheric gases, the nitrogen, oxygen, neon, all of those. When you're trying to get that nitrogen, methane, carbon dioxide, ethane, that pore plot is a packed column that does the separation of those light compounds. And then if you typically with those, you may have to use a second module to get the heaviers, a second column, something more like an OV1 or a DV1, that type of thing. Anything to add to that, Chris?
I guess just emulsive that we could add if you wanted to.
Yeah.
Speciate the oxygen and nitrogen components.
Yep, exactly. So you just
Oxygen from the nitrogen.
oxygen from the nitrogen, yeah. And so keep in mind on your plots and your pore plots, there's different flavors. There's Qs, there's Us, that type of thing. And each one has a little bit different separation. So you want to pick the right one for your application. Anything else, sir?
That's it.
All right. Well, we appreciate it, everybody. Hope this was good for you. Again, we're going to continue to do these monthly. Next month is going to be our gas measurement 101. So we're going to look at the volumetric side. So please join us for that. Let anybody know that you think might be interested. And as always, if you didn't get your question answered, if you've got questions or input or thoughts, don't hesitate to reach out to any one of us. We're all available at any time for a phone call or an email. You go to our website, you can find a way to get in touch with us. And we appreciate it. Appreciate you taking the time, and we'll see you on the next one. Thank you.
Thanks, everyone.